My learning objective is 3.8, and it states that the student is able to identify redox reactions and justify the identification in terms of electron transfer. We will use science practices 1, 2, and 7. 1 will be used to make 3D models of redox reactions, 2 will be used to balance redox reactions, and 7 will be used to connect our topic to electrochemistry. Enjoy the video.
T minus 7 seconds.
Bill Nye the Science Guy.
Hello students, my name is Bill Nye, and today we will be learning all about redox reactions. The name redox comes from two different reactions taking place, reduction and oxidation. When a molecule gains electrons, it is called reduction. When a molecule loses electrons, it is called oxidation. Let's use science practice 1 to demonstrate a reduction and oxidation reaction through the use of Play-Doh models. For example, take the reaction between zinc and hydrogen ions. The zinc will be oxidized to zinc 2+ because it loses 2 electrons. On the other hand, the hydrogen ions will be reduced because each one gains an electron, allowing them to form hydrogen gas. Next, I will teach you how to balance redox reactions. Let's go to the chalkboard. We can use science practice 2 to balance the redox reaction with an understanding of simple math and chemical reaction balancing. Say we have a redox reaction between a dichromate ion and iron with a +2 charge. The first step to balancing is to separate the equation into its reduction and oxidation reactions, or half reactions. We can see that iron 2+ is oxidized as it goes to iron 3+ because it loses an electron. To balance this half reaction, we simply add an electron to equal out the charges. The second half reaction, however, is a bit trickier. First, we balance the oxygens by adding water to the opposite side. Because there are 7 oxygens on the reactant side, we add 7 waters to the product side. Next, we balance the hydrogens by adding H+ ions to the opposite side. Because there are 14 hydrogens on the product side, we add 14 H+ to the reactant side. Finally, we balance the charges by adding 6 electrons to the reactant side. Now that the half reactions are balanced, we multiply the first reaction by a factor of 6 so that there are an equal amount of electrons in each reaction. Once we do this, we can cancel out the electrons and combine the two reactions, giving us our final balance equation. But where can these redox reactions be seen? A voltaic cell is a perfect example. For the voltaic cell, we use science practice 7 because we are connecting an electrochemistry topic to our current research topic of redox reactions. We have solid copper in one beaker and solid silver in another. Connecting the two is a salt bridge, which allows for ion flow and a constant voltage. Additionally, a wire connected to a voltmeter allows for electrons to flow from the anode to the cathode. In this cell, copper is the anode because oxidation happens there, while silver is the cathode because reduction happens there. Therefore, the electrons will flow from the copper to the silver. Although this example is quite basic, voltaic cells are still the basis for very powerful batteries, such as the lithium-ion batteries and Teslas. Now that you've learned all about redox reactions, let's try an example. Go ahead and balance the redox reaction between SO32- and MnO4. Mr. Bonai, is this the right answer? Correct. Well, that's all for me today. Hopefully you now know everything there is to know about redox reactions.